Good evening, ARO attendees. I'm Dr. Sunil Puria. I'm your president this year, and it's with great pleasure that I extend my warmest welcome to each of you to this really our sort of honorary, prestigious award ceremony. It's really something I always look forward to every meeting. ARO is really privileged to have membership that embodies the pinnacle of excellence, characterized by this contributions and numerous accomplishments in this field. And today we gather here to honor the remarkable accomplishments of select group of our esteemed colleagues. And we want to thank all of you who've nominated them. There's a whole nomination committee behind all the speakers, and every year we select some of the, somebody we want to honor. So thank you for coming to this this evening to celebrate them. Your presence really is really important to, otherwise it's not a real celebration. So, so I want to start by first awarding our Poster Blitz winners. In the postdoc category. Poster Blitz are, I don't know if you know, but it's really a fast-paced live presentation. I think it used to be 3 to 5 minutes, something like that. 3 minutes? 3 minutes. It used to be 5, but it's now 3 minutes. And Poster Blitz winners are, applications are reviewed by the Poster Blitz organization. And by the way, I have nothing to do with it. I really don't. And this will become very important in a second. But I did go to some of them, and they were great. So in the graduate student category, our first place winner is Gabriel Alberts from my lab. Thank you, Gabriel. Second place is Amanda Berlingari from UW. Yeah. There's Gabriel. And then third place winner is Paul Secchia, one of our SHBT students. Both of these are SHBT students at Harvard. So third, Paul, welcome. I absolutely had nothing to do with it, okay? And then our postdoc winner category, that's another category of postdocs. Used to be, they were all together, now we have separate categories. First place winner is George Ordway from Zuckerman Institute, Columbia. Second place is Isaiah Spurber from Stanford. And finally, we have Lakshay Khurana from the Institute of Neuroscience at University of Göttingen, University Medical Center, Göttingen. So really, congratulations. It's a very fun part of ARO now, and I'm glad we do it. And we get to hear a broad spectrum of science from the posters. Next, I'd like to invite Marina Silvera to the stage to present this year's ARO Scholarship Awardees. Welcome, Dr. Silvera.
So we are very happy to announce the ARO Scholars of this year. But first, just a little introduction about this program. So the ARO Scholar first started in 2023, and it's a program that's focused on providing opportunities for undergraduate students from underrepresented background to come to ARO and present their research. So this is fully funded for them coming to ARO and present their poster or give a talk. And they also get a stipend to do research over the summer. So the ARO Scholars started as an initiative from the ARO Diversity and Minority Affairs Committee. And the goal with this program is by investing in those young scientists to come to ARO and have a more solid foundation in science, is to have a long-term goal to hopefully increase diversity among academic and clinical roles in the future. And I just want to highlight that the ARO Scholars is fully funded by donation money, and I heard that a lot of this money come from ARO members, And I hear that we have a live link right now, is that
Yes,
right?
yes.
That people can donate and contribute for this program, so hopefully we can keep that going in future years. So, as I said, we are very happy to announce our scholars. And the first one is Michaela Afuzon. She is our first ARO scholar, and is from the University of Maryland.
Thank you.
Okay, our secondary scholar is Amelie Valles. She's an undergraduate student at Johns Hopkins University. Our next ARO scholar is Davia Williams. She's an undergrad research assistant at Vanderbilt University.
Thank you.
We also had a fourth ARO scholar, Daniel Acevedo, but unfortunately he had problems with his visa, so he could not come to ARO to attend the meeting. But hopefully he's going to be able to come next year, and he's going to be receiving his certificate and everything. But stay tuned to see his poster at ARO next year. Thank you.
Thank you very much. I want to say something else. By the way, the ARO Scholars Program was started several years ago, and I believe it was with Ruth Ann when she was president, and several ARO presidents have really promoted the scholarship, and I'm really happy to see come to fruition here at the last meeting and this meeting. And so we are planning to submit a grant, and our 25 grant, and Janine Holt she's leading that effort. And to show some track record, when you apply for grants, as you know, you gotta do preliminary data. So we're kind of having a track record so that, and one of the ways we as a society can help is that we have this fund set up, right? As you mentioned, Maria. So that fund, you can contribute to it. In fact, I just contributed this afternoon, just so I could say I did it. I've been wanting to do it for a long time, but I finally did it. So you can contribute, and then that will help us pay for the next set of scholars, and that says the society supports it. That's the message we send to everybody at the NIH and IDCD, and everyone in general. So thank you. It would be great if you can support. It is now my pleasure to welcome Melissa Carras, and she's the yes, please. Dr. Karras is our 2025 Geraldine Dietz Fox Young Investigator Award recipient. This award recognizes accomplishments and promise in research related to otolaryngology in areas represented at this meeting. And so Dr. Karras is awarded for her contributions to the understanding and mechanisms underlying auditory perception and learning. And so there's a lot going on there for you. That's a broad field. And Dr. Karras will be will present during the Young Investigator Luncheon tomorrow at 12:30. So please attend her presentation. You'll get to learn more about her amazing research. So welcome. Thank you. Great, thank you. All right, now it's really my pleasure to present I'll introduce Zhengyi Chen to present the Award for Clinical Innovation. This award recognizes a body of work that constitutes a significant advancement relevant to clinical practice in hearing and vestibular disorders. Dr. Xu is awarded for his collaborative and continued commitment to research advancing the development and investigation of gene therapy treatments for hearing restoration, and you heard him speak last year at the Presidential Symposium on the OTOF, and you'll hear more about that later. Please join me in welcoming Dr. Jingyi Chen, my colleague at Mass Air, to the stage who will introduce our recipient, Dr. Yulai Xu. Let me start this for you. Oh, no. That's his presentation, but.
Okay,
Oh,
yeah,
but-
no, I don't have a presentation. All right. So thank you very much, Sunil. It's a real great privilege to stand before you to introduce Dr. Yulai Xu, the recipient for this year's ARO Award for Clinical Innovation. So in the history of audit research, there are really a few moments that redefine what we believe is possible. The moment not only advance science, but also transform lives. And Dr. Xu has really given us one of those moments. So I first met Eli as a postdoc fellow in my lab, the Eaton Peabody Labs at the Mass Eye and Ear. Even then, his curiosity, the tenacity, and the deep commitment to bridge research and clinical care made him stand out. Over the years, I have had the privilege to watch him grow into one of the most innovative physician scientists in our field, and today we celebrate his groundbreaking achievement, leading the first successful gene therapy trial for otoferlin gene-related hearing loss, restore hearing in congenital deaf patients for the first time since cochlear implant that was invented over 60 years ago. For those who have ever worked on translation medicine, you know the turning the promising therapy into real treatment for patients is not just about good science. It takes leadership, resilience, and the unwavering belief that breakthrough is possible. Eli embodied all the qualities from developing the minimally invasive surgical procedure to designing precise microleader for gene delivery, from navigating regulatory hurdles to ensure the safety of every patient treated. His vision and execution had set up a new standard in our field. I will never forget the moment when I realized the impact of his work. The first patient who had lived his entire life in silence turned to her mother, hearing her voice for the first time. There wasn't dry eye in the room. And this was just the beginning. Dr. Xu and his team have since treated over dozens of patients, from children to adults, with nearly all experienced life-changing improvement in hearing. So his work has published in all the top medical journals with worldwide coverage and described one of the medical breakthroughs in 2024. But beyond those headlines, what truly sets him apart is his commitment to making sure the technology reaches those who need it most. So he's spearheaded the effort to get all the experts from all the institutions to establish the otoferlin gene therapy consensus, to lay the foundation for the future of hearing restoration. So innovation in medicine is not just about science, it's about courage. The courage to challenge the status quo, to push forward when the path is uncertain, to see before anyone else what's possible. Dr. Yulai Xu embodied all the spirit, and today we honor his vision, his perseverance, and his profound impact on the lives of patients and the field of auditory research. And he is a real shining example of the next generation of physicians and scientists who will usher in a new era of transformative medicine of patients with hearing loss. So please join me in congratulating Dr. Yulai Xu, the recipient of 2025 ARO Award for Innovation and Clinical Innovation.
So the slides are ready.
Hello, everyone. Thank you. Thanks to Sunil, thanks to Zhenyi and everyone, and my team. 5 of them are here today. It's my great pleasure and honor to receive these fantastic awards. And I will give a presentation, Gene Therapy for Deafness, We Can Do More. I'm a physician scientist, and my clinic specialized in autology and neurotology. And my research mainly focuses on gene therapy and translational medicine for hearing loss. And in 2004, I got my MD, and between 2010 to 2014, like Zhengyi said, I did my part of a joint training PhD program and postdoc in Mass Eye near Harvard Med School in Dr. Zhengyi Chen's lab. And I went back to an ENT hospital, Fudan University in Shanghai, China, in 2014. As we all know, about 20% of world population, around 1.5 billion population, suffer with hearing loss. And hearing loss, it impacts speech, language, education, social isolation, and mental health, and so on. As Heno Kiner said, blindness cuts us from things, and deafness cuts us from people. And to be cut out from hearing is to be isolated indeed. About 26 million congenital deafness and more than 200 deafness genes already identified. There's any clinical drugs to treat. And gene therapy, such as gene replacement or gene editing, provides a promising hope for treatment. And there are several advancements. One of most of genetic deafness is monogenic, and we can do local injection with a very small volume. And however, there are some challenges for gene therapy in deafness. First one is the cochleal. The cochleal localized in the deep anatomic position surrounded by the bone. It's very hard to deliver precisely. And there are so many different genes expressed in the different cell types, and how to use the effective treatment strategy, and how to perform clinical translation. And to develop and translate, we did drug components, AV vector production, safety and efficacy in mice, and safety study in non-human primates. And we developed and optimized the inner ear delivery routes from small animals to large animals like monkey, and then transferred to, and then utilized and cadaveric specimens, and finally to the human. And we also designed the very tiny macro injection devices, which used endoscopic through the external auditory canal with a very minimally invasive way. One of the targets is autophagy. Autophagy-related deafness we call DF1B9 is a congenital CV02 completely hearing loss, and it influences 2 to 8% of patients suffer from genetic hearing loss. And however, the autophagy, the size over the single AV capacity. So to date, the delivery of large genes, many carried by dual or multiple AVs. And in 2019, Larry and Alan's lab utilized the DNA recombination strategy and developed the dual AV strategy for the autophagy gene therapy, and which significantly restored the hearing on the knockout mice. And our lab not only confirmed, verified the DNA recombination strategy, we also developed a novel dual AV strategy, use the inter-transplicing on the protein level, and both of them can restore hearing with long-term, both on the neonatal and the adult stage. And after the safety study, there's no upper voice toxicity, and we applied the clinical trial. And after ethical improvements and the clinical trial registration, and the first trial is unilateral. And the general principle is safety is the first consideration. So that's why the patients we choose from older to younger children. And the first, as you can see here, and the first 3 patients are all older than 3 years. And we wait at least 6 weeks to observe the safety, the DLT, the dose-limiting toxicity, and then move to next patients. And there's no any dose-limiting toxicity and serious AE. And for the hearing, and all the hearing, we choose the first control, their average is higher than 95 dB and the baseline. And for the patient 1, and the hair restored to 45 dB at 26 weeks. And for the patient 3 to 6, they can restore to 48, 38, 40, and 50, 55 dB at 26 weeks. And the patient 2, there's no hair restoration. And besides the hair restoration, we also observe the speech perception improvements. So I will show several videos here. You clearly see the patients. They don't have any response to sound, and they cannot speak at all before treatment and after treatment. And the patients can start to have a response to sound, and gradually they can learn to speak. There's no response to sound before. And even 2 weeks after treatment, still no response. 4 weeks after treatment, and he can turn back. Where is the night? I love mommy. So six months later, and he can start to speak. And 8 months, he can speak a sentence. Right now, he's 1.5 years old, and he can speak much better gradually. And the patient 6 is 1 year old, and because we are already older children, and then move to the younger, because we know the younger we treat, and the younger, and the better they can speak.
刘月新，
No any response to sound.
李瑞欣，
And 6 weeks, and he can respond.
叫爸爸，说奶奶，爷爷。李瑞欣，你说苹果，香蕉，你说爸爸买玩具，你说给爸爸打电话，
给爸爸打电话。
你怎么打电话呢？你说。
He can dance with music. So his language improved much better than the patient 4, and he's younger. And he is already 1.5, more than almost 1.5 years after treatment, and his language big capabilities is like the similar regular children with the same age. And he can speak also both Chinese and English. And after the unilateral gene therapy trial, we applied the bilateral trial because we want the people have the localized sound localization ability and better speech perception in noisy environments. So still, the safety is the first consideration, and that's why we choose the first patient. He's 11 years old, and after treatment, there's no any dose-limiting toxicity and serious AE. And after treatment, and both year had hair restoration and speech perception improvements and sound social localization restoration. And these two videos show patient 1 and patient 3. 4 weeks after injection, she can respond to the different frequency. Now she can start limited language after language training. That shows the sound localization taste.
Lại nhớ. Rồi, mã.
Which one is the horse? Which one is dark?
对，鸭子。对。
Yeah, the final part means she can understand and recognize which animals. But still, as we can see, 11 years old without any treatments, and language is very limited. That means the age is very critical. We really have a very critical period for language development. And I will show the last video.
Yeah.
No any response to sound?
Yeah.
And start to respond to 3 weeks after injection. And start to dance with music.
Chào mama.
Mama.
Chào nana.
Nana.
Chào爷爷.
爷爷。
你帮我找一找芒果。
妈妈帮我找找芒果。
He can speak a sentence 1 year after treatment. It's in noisy environment. Okay, to summarize, this is the first in-human clinical trial with gene therapy for genetic deafness, and it also is the first in-human clinical trial of dual AV gene therapy, which means for the large genes, we can use this strategy for human. There's low DRT and serious AE occurred, and 10 of 11 children showed hearing restoration. And, hearing was restored in time-dependent manner up to 6 months. And after 6 months, and the hearing maintained very well. And speech perception was improved in patients who had hearing recovery, and the ability of sound socialization was also restored in patients with bilateral treatments. And here I want to show some original data. As we can see here clearly. You can see here this is the other year without treatment, the ABR, and this is after treatment. And the patient 3 and the patient 4, the start means with treatment. And the AHR, as we can see here, without treatment, with treatment, without treatment, with treatment. And especially for the patient 1, right now is already 2 years and 2 months. And as we can see here, without treatment, the ABR with treatment and the ASR without treatment, with treatment, and the PTA. This is the year without treatment, this is with treatment. And right now we have 1 patient already have 2 years follow-up, and 5 patients with 1.5 years, and all the 11 patients with 1 year follow-up, and all the hearing maintained very well. Actually, we also did the adult patients treatment. She is 32 years old, and one side with cochlear implant, and this side we treated with gene therapy. And she told us she can hear even 5 days after treatment. And as you can see here, this is baseline. There's no the higher than the 95 dB. The ABR, ASR, and the PTA. And after treatment, you can see here the year with treatment with STAR. So our goal is from bench to bedside. So in 2014, when I was in Mass Engineer, so Dr. Chen and collaborated with Dr. David Liu. So we did the first study of gene editing in a year, and then when I go back to Shanghai, so we did several works to treat different genes like myosin 6, and TMC1 use RNA knockdown strategy. And myosin 6 is DNA neighbor. We use knockout mice, and the KRH18, which they gifted from Karen Steele, Dr. Karen Steele. And we use the HRL, the repair strategy. We also rescued the heron. And the KCNQ4, we tried the knockouts and the base editor strategy. Both of them works. And for the myosin 6, we also use the RNA base editor strategy. And autofolding, we both tried the protein recombination or DNA recombination. And then we finished the preclinical trial and then moved to the first in-human clinical trial. We also did the MPZL2, use the gene overexpression or gene editing. And we also tried DNA-based editing for autofolding mice. But as we know, the gene replacement is suitable for all autofolding related patients, but the gene editing is specific of the mutation. So that's why we use the gene replacement strategy. So there are still some opportunities and challenges. The first one is how to precise inner ear drug delivery. First of all, the AAV, the Victor AAV, the packaging limits, we need to develop a cell-specific target. And we also need to develop a long virus, like AMP-VRP. And the surgical approach, we need to develop a standardized and a simple approach for doctors to deliver the gene therapy drugs with most minimal invasive way. And in our clinical trial, we did the fenestration on the stapedial 40 plate. So the question is, the study still required whether the fenestration is necessary. If there's no need to fenestration, where we make the injection much easier. And we also needed to develop the standardized and minimally invasive delivery devices. There's no any commercialized delivery devices for our ear. It's really, for the eye, they already have, but there's no, for the ear, we don't have any. And for the clinical trial and the challenge, there's the age and the severity of hearing is really most important, and what's the time window, and how to protect residual hearing. Because this is the first in human clinical trial, we choose the patients with really profound or complete deaf. But in future, how can we choose? If the patients have residual hearing, how can we choose? And especially for the other patients, the progressive hearing loss, how can we do that? And also long-term safety and efficacy. Right now, it's still the follow-up is not enough. And for the AAV neutralized antibody, is the pre-existing neutralized antibody limited efficacy? And can we do the repeat administration, or this year we treated, and how can we do another year? And for the comparison between gene therapy and cochlear implant, which already more than almost 60 years, we need comprehensive and systematic compare clinical trial to compare. And the other thing is as we said, more than 200 definite genes. And for the specific gene, the number is is low, it's kind of low. We call it rare disease. And the rare disease, to develop the gene therapy is time and money consuming. So many companies, they don't have commercial interest. So it's make this, it's very hard. So we call for the collaboration between academic, industry, government, and the society. And also in some low and middle income countries, lack of genetic screening. And however, almost 80% of hair loss population is in the low and the middle income countries. And finally, I want to thank SOAR for collaboration from Professor Huawei Li, Wuqing Wang, and Bin Chen from INT Hospital of the University in Shanghai, China, and Professor Zhengyi Chen from SNE Harvard Medical School, and Njie Chai from Southwest University in China, and especially the collaboration with the industry, reference gene therapeutics, and ultrafolding. This is just on the first gene we carry. This is just beginning. We have more and so many genes. So we still need to do more work. And I would also like thanks to our team, and 5 of them are here, and both basic research and clinical research members. They are teamwork and diligence. And finally, I would like thanks to the patients in our clinical trial. Thank you very much.
Thank you very much. Great, thank you, that was amazing. There's indeed lots to do there. So next we recognize the 2025 Pioneer Award in Basic Science, and the recipient is Xiaoxing Wang. The Pioneer Award, just a few words about what that means. Award in Basic Science recognizes a body of work representing a significant advance in hearing, vestibular, or related science, and established in the awardee's own lab. Okay, so Professor Wang is awarded for his pioneering work to establish the marmoset model to elucidate the neural and behavioral basis of hearing and vocal communication. And in fact, I remember hearing your talks many, many years ago, so I always remember them. Please join me in welcoming Stephen Eliades to the stage, who will introduce our recipient, Professor Xiaoxing Wang. Thank you.
Well, thank you very much. It's my great pleasure to introduce Xiaoxing Wang as the 2025 Pioneer Award in Basic Science for the ARO. Xiaoxing is a professor of biomedical engineering at Johns Hopkins. He received his PhD with Murray Sachs, doing work in cochlear nucleus at Hopkins. Then he went all the way over to UCSF to work with Mike Merznick to study somatosensory cortex primarily. Thankfully, he came back to the auditory system when he started his own lab in 1995 to look at auditory cortex and related behavior. I had the pleasure of being one of the 40 postdocs and graduate students to have gone through Xiaoxing's lab over the last 30 years, which is an incredible contribution to our field more broadly. But what we're really here to talk about, in ways we recognize, is this development of the marmoset model. I suspect I'll talk a little bit more about what marmosets are, but briefly, they're small, non-human primates. They're natively from Brazil, but have a number of advantages, including a human-like hearing range and rich vocal communication. I was there when he did his first awake marmoset recording. I don't know at the time. It was a very exciting time. We had no idea what we were going to find. I don't know at the time if he had a sense of where this was going to grow. He'll talk a little bit more about the science he's done in his own lab, but what I thought I would briefly talk about is the broader impact that marmosets have had on the biomedical research community. Marmosets are an explosively growing model species. At the time he started this lab, they were almost unheard of. But now they've had profound influence in a number of areas, including neuroscience, genetics, immunology, to name a few. In fact, the number of labs working with marmosets, the amount of grant funding has more than doubled in the last few years alone. Marmosets, for example, are the first non-human primate species for which we have transgenic lines available, although they are still somewhat limited. I think, moreover, Xiaoqing has always brought an enthusiasm to science, which has been very infectious. He may not remember this, but in those early days, I remember being in the lab late one night trying to create some stimulus sets to present to the marmosets to do these recordings. It was probably 8 o'clock at night, something like that. And the lab phone rings, because we didn't have cell phones at those days. At least I didn't. And it's Xiaoqing. He's at home having dinner. No, he wants to come back in because he wants to get these stimulus sets done, because he wants to try them tomorrow. And he came back in, and we did, in fact, get them done by the morning. So anyway, without further ado, it's my profound pleasure to introduce Dr. Xiaoqing Wang as the 2025 ARO Pioneer in Basic Science.
Start from here.
Oh.
I think we just go. It's yours, right? Okay.
You can use the clicker if you like. Forward, backwards.
Okay. Well, thank you all. It's a great honor to receive this award, and the honor really goes to everyone who I've worked with in the past 30 years. So I come to this country as graduate students in 1985, January 2nd, 1985. My flight landed at Detroit Airport. I went to University of Michigan as a graduate student to study for my master's degree in electrical engineering and computer science, and I saw the snow on the ground for the first time in my life. I grew up in the southern China, never had snow. Then in Ann Arbor, I got exposure to neuroscience, become intrigued by how the neuron in the brain fire action potentials. Then I went to Johns Hopkins in 1986, did my PhD there. It is there I become interested in how the auditory system processes speech. As you all know, speech is one of the most important things that our auditory system processes with. Then, after my PhD with Murray Sachs in Johns Hopkins, I went to San Francisco to do my PhD postdoc with Mike Merzenich. Then I began to think about what I would do if I get my job somewhere later on. Because I have a profound interest in how the brain processes speech, I asked myself in the middle of my postdoc in 1993, which model system to study. At that time, the prevailing model, the very popular, successful model, are songbirds and echolocating bats. But my ultimate interest is to understand the human brain. So I thought I would like to study a species that are closer to humans, that is non-human primates. Some of you would know in our Earth, monkeys are only distributed in certain continents. For example, in Asia, there are Old World monkeys, and in South America, we have New World monkeys. And the South American continent drifted away from the rest of the world 35 million years ago. But there are other monkeys. The most popular monkey, standard monkey model at then and still now, is macaque monkeys. This is one of the Old World monkey models. Then there are other monkeys like owl monkeys, squirrel monkeys, so far and so on. And I had the privilege of working with some of the species. I went to the library, learn which monkey species would be most suitable to study vocal communication, and eventually I conclude it is marmoset. For the reason I will explain in a few minutes. This was perhaps the most professional decision I made in my career. But why marmoset? Marmoset originated from Brazil in South America. It's living in an environment like this, heavy vegetation. Here is a wild marmoset in the middle of the forest. there would be another 12 or 15 of them living on the trees as a group. So they are highly social primate species. Because in this environment, visual communication is impaired, you don't see each other, they have evolved to have a very rich, interesting vocal repertoire, as you can see here, that is reminiscent of elemental speech that we as an electrical engineer are very familiar with. These are the vocalizations we recorded in our colony in Johns Hopkins. So marmoset is one of the very few primate species that remain vocal in captivity. This is very important because that's where we do experiment. There are several other features. For example, marmosets are highly reproductive. They give birth twice a year. Every time is twins, sometimes triplet. They have a short development period. They reach sexual maturity in 18 months, year and a half. Therefore, a graduate student with 5 to 6 years lifetime could track 3 generations. They are small animals, about 400 grams. The lifespan is only 10 years. So these species, you can study the entire life cycle under the roof of one laboratory from birth to death. Also importantly, as you can see in a few minutes, they have a flat brain that's ideal for imaging cortex. Even more importantly is that marmoset is feasible for genetic manipulation as perhaps the only primate species that can be done in larger scale. So marmoset has a similar hearing range as humans. They pretty much hear what we hear, including our speech. Now, in humans, when we perceive vocalization, speech, we have this phenomenon many of you are familiar called categorical perception, or equivalently, we call it perceptual mechanism effect. And then we have done the test that marmoset, when they perceive their own vocalization, they show the similar perceptual mechanism effect as we do in humans perceiving our speech. They share some common properties with us. Marmoset brain shown here on the left is similar to that of other monkeys and similar to humans, particularly in auditory cortex, which I show here with the red dots. Now, more than that, in auditory cortex of primates, people have been showing there are 2 pathways: the dorsal pathway for process of what information and the ventral pathway for process of word information. And in humans, auditory dorsal stream is involved in auditory motor integration, sensory motor control, and vocal production. Our most recent study comparing marmoset, macaque, and human brains shows the connectivity strengths of the dorsal pathway in marmoset are actually more similar to those in humans and much stronger than that in macaque monkeys. So all of this makes marmoset a very interesting model. So in last 20-some years, my laboratory at Johns Hopkins has taken 2 approaches with this model system. First, we use the marmoset model to study fundamental neuron coding principles in audition, the problem of hearing. Second, we use this as a neuron ethological model to study the neuron basis of vocal communication in primates, this is speaking. Until marmoset model, you could only do such a study in sunbirds and echolocating bats. Now, when I started at Hopkins, I have a small lab I can show here. I have my first graduate student, Tom Sulu, my first postdoc, Ross Snyder, my first visiting scientist from China, Li Liang, my first technician, Ashley Pistorio, and here is Steve, who just gave an introduction. Steve was in his younger days as an undergraduate, later on stay on. So with this small team of dedicated, passionate scientists, young scientists, we move on to study and build the marmoset model. At that time, the popular way to study cortex is to anesthetize the animal, open the skull, where you can put many tracks of penetrations to record it from a neuron. This is one of the studies I did in postdoc when I was at UCSF. Animals the anesthetized. But soon I realized, after spending nights in a laboratory, that once the animal is anesthetized, auditory cortex is very silent. And so once I started my lab in Hopkins, we began to develop a wake preparation. In this case, we trained the animal to sit in a chair for a couple of hours, and we drill a tiny hole, miniature holes under microscope about 1 millimeter in diameter, from which we can put 5 to 10 penetrations. We spent 1 week recording whole, and whole by whole in the time course of several months a year, we can map entire cortex in clinical condition. Now, when we and others recorded from anesthetic cortex, we all know that the cortex was quite silent, as shown on the left. But once we start recording from animal in weak condition, we can drive neuron in a very lively fashion. And we've soon learned actually neuron in outer cortex is a far more selective complex than previously known. But if you drive this neuron with a peripheral stimuli, you can drive into sustained firing. Later on, we take these techniques, develop even more challenging approaches, like intracellular recording in weak marmoset. We published a couple years ago. And we have developed techniques to implant the electrode in marmoset brain. This is work that Steve started when he was in my lab. And later on, we put a wireless transmitter on this so that we can record from freely moving, vocalizing marmosets during social communication. So more recently, we have taken the advantage of a flight brain of a marmoset, developed the techniques we call it through-skull optical imaging. Without opening skull, without even thinning this, we can record intrinsic activity in marmoset brain, showing auditory response, somatosensory, motor, visual response. This is really a marvelous species. It's the only species of large size that allow you to record through the skull. Okay? So step by step, over the years, we have developed all the major techniques for physiology and behavior in marmoset. So now, as of recently, we can see most neurophysiological techniques available in weak behavior marmoset. Some of you who notice my CV knows that our first marmoset paper comes 6 years after becoming assistant professor. It took us a long time to develop a new model system. I almost did not get him a tenure, but Hopkins was a patient place and let us try. So the approach we're taking is a systematic, long-term approach to tackle key scientific questions. So along the way, we have made a number of interesting discoveries. For example, we have identified pitch center in marmoset cortex, and others work on human and show there is a mirror center in human cortex that also processes pitch. So we know the processing of pitch, which is the element of speech and music, is not unique to humans. We also show that marmoset perceptually share primary features of complex pitch perception as humans. All those 3 gold standards of pitch perception that evaluate in humans will demonstrate they exist in marmoset as well. So what's the implication of pitch processing in species other than humans? Marmoset, as New World monkeys, bifurcated from human lineage 30 million years ago. That's a long time ago. In humans, we only have music very close to us. The oldest instrument is 40,000 some years ago. So the discovery of pitch processing mechanisms in a species so far away from us, such as some of our capacity to perceive music element may exist long before we evolve to modern humans. So in short, with many years of work, us and others, we have formally established marmoset as a useful and potentially productive model for auditory neuroscience. Now, some of you notice this particular picture at the beginning. Now, when I tell you what is this. So on the left is a human cochleogram when humans listen to sing of opera. On the right is a simulation of a marmoset cochleogram. As you can see, when you sing opera to marmoset, while their ear is not as fine-tuned as humans, they can hear pitch. They can hear the contour of melody. Okay. Now, outside addition, there has been rapid growth of marmoset research. In 1995, when I started, we're the only lab in the States that devoted entirely to marmoset. So over the years, that number grew, and as of 2023, there are over 25 marmoset colonies, 50 labs. Several years ago, NIH established 4 national marmoset breeding centers to breed marmoset for the scientific community in the United States. I'm leading one of that effort. And several years ago, NH also funded 5 transgenic marmoset projects in the country, including one in Hopkins I'm leading. And we're producing genetically modified marmoset for disease models for studies. Now, NH also set up a marmoset coordination center, so not any of you who want to use marmoset, go to this website, submit an application, then you'll receive a marmoset shipping from one of the 4 centers. So marmoset has now risen to be one of the 2 major non-human primate models in neuroscience research, being marmoset and macaque. So these are the places in the United States, Canada, Europe, Japan, Australia, and China that has marmoset programs. And many of us believe marmoset are a keystone model to understand and cure human disease in the 21st century. Okay? Many questions can be studied in marmoset besides audition, vision. There are 2 very important points for marmoset, that is development and aging. Of course, genetically modified marmoset has great potential. Currently, there are 80 models, autism models. In coming years, you will hear more. So if you're interested in marmoset as a model system, you should ask yourself, what are scientific questions you want to ask that takes full advantage of marmoset? This is what we did for audition. Okay. So what are we up to for the next 10 years? We want to continue to study marmoset, but we want to link our study in marmoset closer to humans. That's where I started as an engineer, that I want to understand the human brain ultimately. So one of the things we want to do in the process of doing this in collaboration with engineers and computer scientists is to set up a large-scale automatic social behavior analysis in our colony. Our colony has tens of dozens of animals. We'd like to study them all together, wire them with microphones, cameras, and transmitters for their brain activities. Marmoset had very interesting features. As you can see from the video on the lower right, this marmoset is playing an iPad, and we're training this marmoset to discriminate sound, but without any food reward. Now, you all know for animal study, it is standard to deprive animals of food and water and push them to learn. But we as humans, when iPhone come out, people realize you can play iPhone whole day long without eating. And we think there's some evolutionary tree, not besides humans, marmoset may share. So you can just see this marmoset, play with this non-marmoset, come along, and the first marmoset, I think as a parent, will push this animal away. This work was done in Beijing, in Tsinghua University, where I hope to establish a new marmoset facility in that university. So we believe marmoset could be a model for us to poke into higher level of cognition of humans. That's curiosity-driven, not food-driven. Now, another big question we'd like to tackle in coming years is a question many of you in this audience would be interested. That is, what is the functional organization of auditory cortex beyond the tonality? In vision, you all know from the textbook, we have this human visual model of V1. But in audition, this is what we have, just tonality. But tonality is not special for cortex. So several years ago, my former graduate student, Lei Feng, did this work, identify neurons in auditory cortex that are selectively respond to harmonic patterns, not tones. And with the mathematical tool, Lei's work shows these neurons' transfer function is not one frequency, but several frequencies, harmonic related. We call this neuron harmonic temporal neuron. This could be the neuron if they exist in humans, that they listen to piano, keyboard being played. What's interesting is that these harmonic temporal neurons are widespread in auditory cortex. The pitch neurons are restricted to small region. So with this evidence, and we propose perhaps a functional organization of auditory cortex is by harmonicity. This is reasonable because you think about evolution and development, harmonicity is everywhere in our hearing environment. So it is possible that it's being imprinted in our brain. We're actively working on this hypothesis. Now, last, I want to see that in audition, besides speech, the next, perhaps even more interesting question is music. Let me show you a video showing you what's happening to the marmoset brain if we play a piece of music that you are familiar with. Now what you're seeing is a recording of calcium imaging of a marmoset response to music. A different area of cortex light up when different element of music shows up. And some of this bright spot are pitch neurons, some of harmonic neurons, some of neurons we have yet to identify. So entire autocorrect marmoset is in this video because it's a flight bird. Okay, but many of you will argue, animals listen to music sound, but not the music. When we listen to music, we have emotion, we perceive the beauty. But why is music beautiful? This is a picture of southern China in Guilin. Anyone knows Chinese culture? This is what we consider the beauty. But why do we listen to music? What is biological basis of music? We believe there are 3 levels of neural mechanism of musical perception, starting with neuron coding of acoustic feature music. This perhaps we can study in species and marmoset. Then the neuron processing of emotion and memory of music. Some of the elements we can study in animals, but not all. But finally, most importantly, neuron aesthetics, the beauty of music. We believe this perhaps can only be studied in humans. So in the last several years, our team began to collaborate with professional musicians to study how the brain processes music in a concert hall. This effort was led by my colleague, Dr. Juan Huang, who is in the audience, and also in the picture here. The showing below here was one experiment we did in Beijing in Central Conservatory Music Opera Hall. When listeners enjoy a real live music play, we record their brain activity projected on the screen here. We have also been studying brain response of musicians while they're performing music. On the left, you're showing a celloist and pianist that are playing music. Both of them are wear F-ear devices. On the right, 2 traditional Chinese musicians play music and wear F-ear. And showing below here a trace of response of musicians as well as listeners. We believe by analyzing their brain activities, we will soon eventually understand how the human brain processes music at a neurological level. Okay. Finally, I want to acknowledge many of the students who have gone through my life, at least here. And I was very fortunate to be able to work with a talented, passionate student in Medford Hopkins. A number of them have moved on to have their own life, showing on the right here. Some of them continue to work on the marmoset that is highlighted by both fund. Our work since 1997 has been funded by NIH. We're extremely grateful for taxpayers' money that give us to pursue scientific questions. And I want to thank all my former students and postdocs, some of them in the audience. Without you, we would not be here with a marmoset model. So thank you all.
Okay, so our journey of recognition continues as we honor the 2025 Award of Merit recipient, which is Dr. Paul Fuchs. Unfortunately, I got the sad news one day, just a few weeks ago, that Dr. Fuchs was unable to join us for this important event this evening. So to speak about his remarkable achievements and the well-deserved recognition he's receiving, I would like to invite Dr. Elizabeth Glatsky and Larry Lustig, who's already here, to the stage. So before I introduce you, before we have you come up and speak, I'm going to introduce you a little bit. Dr. Glatsky completed her training in biology and neuroscience in Germany. She studied biology in Göttingen, received a PhD at the University of Kaiserslautern, sorry, I botched that up, and did a postdoc, I do that often, did a postdoc at Tübingen University of Tübingen, and she started her work in cochlear physiology in 1998. She moved to Baltimore in the US to study with Dr. Fuchs, and together there were key discoveries made in hair cell efferent and afferent transmission. In fact, I use your work in my lectures in class often, as many of us probably do. Since 2002, she has been leading her laboratory at the Johns Hopkins School of Medicine, studying both efferent and afferent synaptic transmission in the inner ear, including type 1, type 2 afferent pathways. Over the years, Dr. Glasky has continued her collaboration with Dr. Paul Fuchs, and together they've provided an assessment of the type 2 afferent fiber activity in the inner ear. Dr. Glasky is the Director of Research in the Department of Otolaryngology, Head and Neck Surgery at Hopkins, and holds the David M. Rubenstein Professorship. And next, I'll introduce Dr. Lustig. Dr. Lustig is an MD, and he's an otolaryngologist who specializes in otology, neurotology, and skull-based surgery. Quite a range of things there. Keeps you busy. Dr. Lustig grew up in Northern California and completed his undergraduate studies at the University of California, Berkeley. He graduated. You have sandals on? No. Okay, you're good. He graduated from the University of California, San Francisco, UCSF, School of Medicine, where he also completed his otolaryngology residency. After residency, Dr. Lustig completed his neurotology and skull-based surgery fellowship at Hopkins University and remained on the staff through 2004. In 2004, he was recruited back to UCSF. We'll see this is back and forth between East and West Coast. In 2004, he was recruited back to UCSF and led the Division of Otology and Neurotology in the Otolaryngology Department. And then in 2014, he was recruited back to the East Coast to Columbia University in New York, where you and I actually we met soon after you got there, and he was recruited to Columbia and New York Presbyterian Hospital, where he practices today as the Howard W. Smith Professor and Chair of the Department of Otolaryngology. And so with that, I'm going to hand it over to you guys. Let's see, do it. You're going to go next first, I think? Okay, here we go. Thank you. Thank you very much.
Thanks, Sunil.
Thank you. Is this okay? I sit here?
Yeah, you're good. You're good.
Thank you so much, Sunil. Good evening, everybody. As you've all heard, unfortunately, Paul has recently completed treatment for a very curable form of throat cancer, and he literally did not have a voice to give this lecture. So he's doing quite well. He sends his warmest regards, and he anticipates being here next year. He's incredibly humbled by this honor, and we hope to actually do an extended version of this talk in about a year's time, which will be a little bit more pointed. We didn't feel it was right to roast somebody who's in absentia. I will be providing an overview of Paul's life and his career, and Elizabeth will be summarizing his research accomplishments. So as all good stories must start, we must begin at the very beginning, in this case, pre-Paul. This is a photo of Paul's parents' wedding in 1947, soon after his father returned from service. Paul's family were farmers and artisanal mechanics. His mother and family were, quote, city folk. Her dad was a linotype operator for the city paper, and there were really no academics in the family before Paul. They settled down in their farm where his father was raised in a small town called Fenton, Missouri. Today, Fenton would be considered a St. Louis suburb, but back then it was much more rural. Fenton lies on the flood-prone Merrimack River, which drains right into the Mississippi. So being good Catholics, Paul's parents eventually had 11 children. Paul was the second, shown here with grandma on the nearby farm, where most of the kids were put to work at a time when the term child labor was apparently not part of the national lexicon. I'm told that this pic actually does not include all of the siblings, and they had some cousins fill in as placeholders. I guess if you have 11 kids, nobody's really going to notice the difference. And here's Paul with his 9 siblings, sometime later, having survived childhood labor on the farm. Paul's the dapper one, second from the left, wearing his signature white dinner jacket. Paul's academic career really started in high school at Del Buffalo Seminary, where he first learned how to tune his own hair cells on the guitar, shown here on the left. In 1969, he was still focused on religion and matriculated at St. Joe's College in Rensselaer, Indiana. The college was founded in 1889 by Father Joe Stevens, and fun fact, was used as the backdrop in the classic sports film Brian's Song. If you're under the age 50, look it up on Wikipedia. So just after 2 years, in what can only be described as an about-face and throwing his religiosity aside, Paul matriculated at Reed College in Portland, Oregon. Growing up in California, we used to refer to it, Reed College, as Weed College because of their liberal attitude towards drug use. In fact, according to Wikipedia, the unofficial motto of Reed is atheism, communism, and free love. Paul, it seemed, fit right in. Here you can see him studying diligently as a biology major. The summer after his senior year, he spent some time in Woods Hole, Massachusetts as a Summer Grass Foundation scholar. This is a place that Paul would return to later in life, as I'll go to in a minute. Here you see a picture of taken sometime later. Paul's on the bottom row, standing out, sporting a classic 1970s tank top with the Falmouth logo. Following a very successful career at Reed, graduating Phi Beta Kappa, he opted to pursue a neuroscience degree at Stanford University. At Stanford, he trained under the great Donald Kennedy, who would later go on to become editor-in-chief of science and president of Stanford, among his many accomplishments. He also worked with Dr. Getting at the time. In this Kennedy lab picture, Paul is looking pretty cool, I think, eyeing what appears to be a potato chip in Dr. Kennedy's hand, cue and starving grad student. And in case you were wondering what was in the tank in the background, appropriately labeled crayfish, likely either the lab mascot or future experimentee. Shortly after this, he would do a postdoc with John Nichols, also at Stanford. Nichols was another icon in neuroscience who wrote the influential textbook From Neuron to Brain, and also did pioneering work in the leech nervous system. Sadly, Dr. Nichols passed away just 2 years ago. Paul would later join John Nichols as a co-editor of that same textbook, Neuron to Brain. Then it was off to Cambridge University after Stanford for another postdoc, and this time with Dr. Richard Fettyplace. I'm sure if you ask Dr. Fettyplace, he will regale you with amazing stories of Paul while he was a grad student there. As anybody who knows Paul, Dr. Fettyplace was an absolutely enormous influence on Paul's career, for which he is forever thankful. Paul also did some extracurricular research while in the UK, which is probably his most memorable and life-impacting work, where he met his wonderful and love of his life, Joe Marvin. Here you see Paul and Joe enjoying a classic English pint. After his Cambridge experience in 1984, Paul then returned to the United States and joined the faculty as an assistant professor at the University of Colorado, ultimately rising to the rank of associate professor in 1995. What should not be a surprise to anybody is Paul was awarded the teaching award by the medical school 5 times while he was a professor there. Then in 1995, he was recruited by Johns Hopkins by Charlie Cummings, where he spent the remainder of his career, retiring just last year as the John Borley Professor and Director of Otologic Research. So I will not be going into substance on Paul's major work, which I'll leave for Elizabeth, but I will say that he has been unbelievably influential in everything he's done. He was really one of the best lecturers I've ever had the privilege of watching, able to distill complex concepts into something that anybody can understand. He has embodied Johnny Cash's anthem, "I've been everywhere, man," having given lectures all around the United States, as starred here, but also all around the world on most of the continents and around the world. He's given a number of distinguished lectureships, including the Martin Lecture at the University of Colorado, the Vandersicht Lecture at the University of Washington, a keynote lecture at the Midwestern Auditory Research Conference, the keynote speaker at the Chinese Hearing Research Conference, and a keynote lecture at the inauguration of the HRI Institute in Paris. In addition to being an unbelievable researcher, he's also an amazing editor, having edited multiple iterations of the Neuron to Brain, the Oxford Handbook of Auditory Science, the Physiology of Mammalian Hearing, and Advances in Comparative Studies of the Inner Ear. He has received citations from the American Otologic Society and the American Neurologic Society. He has been unbelievably active in the NIH, having served as ad hoc reviewer over many years, the Hearing Research Study Section from 2000 until his retirement. He was board of the Scientific Counselors in 2003 to 2008. It was chair of that group from 2006 to 2008, chair of the AUD Study Section, and was a member of the committee that picked Deb Tucci to lead the NIDCD as the most recent scientific director. And for our own great society, he was an unbelievable member and great leader, being a council member from 2007 to 10, president in 2008, and he chaired the finance committee after he stepped down from president from 2014 to 2017. So I want to end the recitation of Paul's major accomplishments with one of his greatest gigs, was running the summer-long biology of the inner ear course at Woods Hole, where he truly returned to his beginnings when he was a summer grass Foundation scholar. In 3 separate summers, along with Stefan Heller, he ran the most sought-after research summer experience in auditory neuroscience. The course featured a veritable who's who of luminaries in the field, many of whom are sitting here today, and teaching the most advanced auditory techniques available for each of those courses at the time. I don't recall seeing Paul as happy as I saw him there, wearing his traditional shorts and sandals and doing what he loved to do best, science and teach. Through all of this has been Paul's family, his beloved wife, Jo, his 2 sons, Toby and Sam. I also want to point out that Paul is the veritable Hopkins man, wearing his ID at home and on vacation wherever he went. On a personal note, I can say that Paul is one of the most influential mentors and close friends I've had in academics, and I can think of nobody who's more deserving of this award than Paul. And with that, I will pass the torch to Dr. Glowatsky, who will talk about his major scientific accomplishments.
Thank you, Larry. I'm really very pleased and honored to give you a very short overview of some of Paul's key research accomplishments, and I will also keep it light because we want to have the real deal next year when Paul is present here. I just want to point out that as a true neuroscientist, Paul has worked with multiple animal models, starting with aplysia, working with the crayfish, then with the leech, and then here on the lower row you see the model systems he has used in hearing science. Turtle, starting with Robert Fattyplace, the chicken in his own laboratory, even some lizard is in here, but then also rat and mice in the end. And his major work has really been focused on the hair cell afferent and efferent synaptic transmission. And just to start at the beginning, as you all know, the sound signal is transmitted to the hair cell via mechanotransducer channels. A receptor potential is created, and then the depolarization of the hair cell activates voltage-gated calcium channels, somewhere down here, and activates transmitter release, which then basically changes the firing rate in the auditory nerve fibers, the afferent synapse. However, there are also feedback loops, efferent synapses, whereby sound may basically through a feedback loop activate an efferent pathway that feeds back onto the hair cell, and through a cholinergic synapse hyperpolarizes the hair cell, as we know now. And this is also a very important pathway. As you know, in the inner ear, the outer hair cells really mechanically amplify the basilar membrane movement, and this amplification is needed for the inner hair cells to pick up the sound signal and send it to the brain. And the efferent feedback modulates the outer hair cell receptor potential and thereby can change this level of amplification. So these are very basic in the sense needed, critically needed mechanism that allow us to hear. Paul started working on efferent inhibition of hair cells in the turtle with Robert Fattyplace and John Art in England. And I will just brush over this and move on to saying that Crawford and Fatty Place really also worked on electrical tuning in turtle hair cells. And Paul, when he opened his own lab, took this topic and kind of started at first to repeat some of these findings, but then basically went his own way. So in chicken, electrical tuning in hair cells is based on the tonotopically varying BK channel kinetics. BK is the potassium channel that is here located at the afferent synapse, and it's kind of a play between the calcium channels and then the BK channels that are activated by calcium influx and voltage that basically electrically tune hair cells in species like turtle and chicken. And Paul spent some years to figure out some of the underlying mechanism in chicken. So splice variants of these BK channel alpha subunit and the graded expression of some modulatory beta subunit along the basilar papilla, that is the hearing organ in the chicken, basically set these varying properties in hair cells that electrically tune them. And so there's a whole series of papers looking at this mechanism with Krishnan Ramanathan, who was a graduate student in the lab, and their first paper was published in Science, and then there were several follow-ups. Secondly, Paul focused on the afferent synapse, really on the function of calcium channel properties. The L-type calcium channels at the afferent synapse are very important with their specific properties. And what's important is that these channels are what's called non-inactivating, which helps transmit the receptor potential truthfully into transmitter release and change in firing rate. If they were inactivating, that would basically be a problem at this synapse. And Paul studied the mechanism of how this calcium-dependent inactivation, or rather the lack of it in hair cells, is constituted, and basically collaborated with others to figure out what are the underlying mechanisms. He also very early on understood that the calcium channels that are very closely located at the synapse, we all know now, if you do an immunolabeling and you do a CTBP2 and a postsynaptic calcium, it's all very colocalized. But at that time, that wasn't really clear. But Paul kind of had the vision to look at the relationship between calcium channel size and ribbon synapse size in chicken, and basically foresaw this tight connectivity. When I entered the Fuchs lab, I brought the mammalian system into the mix, and then over the next several years in Paul's lab, chicken and mammal were studied parallel. And it was quite amazing. There were lots of recordings we would look at where the effects were just identical. You could not tell from the trace which species the recording was from. But what Paul allowed me to do, and that basically attests to his mentorship, he gave me space and freedom and time to develop recordings from afferent endings in the at the inner hair cell afferents. And so it took quite a while to set up this recording, whereby we did patch clamp recordings from the afferent endings. Here you see a hair cell in a DIC picture, and these little things, these are the auditory nerve fiber endings in an excised preparation. And when we were able to record the postsynaptic activity in the auditory nerve for the first time, we saw something very unexpected. We had expected little synaptic events that all kind of looked the same, but they had all very different sizes. Some were giant, and they all had very different shapes. And to make a long story short, Paul and I kind of then try to basically propose that this complex mechanism of release may be a form of multivesicular release. That was basically, it was really Paul's vision that brought all of this together. I went then on studying these afferent synapses, and Paul continuously and returned to working on his efferents. So at that point in time, there were lots of things unclear. It wasn't even clear that there were nicotinic receptors at the efferent synapse. It was thought that the cholinergic response was metabotropic. So he did some key experiments using pharmacology to kind of point in the direction of a nicotinic receptor. And he also, it was known already, of course, from the work of Art and Fatty Place that there was a biphasic response at the synapse when you record from the hair cell and look at the synaptic efferent current. But Paul in the chicken did the experiment where he kind of separated these two phases, which then turned out that this inward current here is the influx through the acetylcholine receptor into the hair cell, and this outward current is then the calcium-dependent potassium channel that is activated through the calcium influx. The so-called SK channels, and they here you see those both next to each other. Both this continued work on this two-channel hypothesis, plus the fact that we were able to record inner hair cell efferent synaptic currents in the mammalian cochlea, which looked exactly like this also, plus coincidentally that the Elgosian lab and colleagues cloned the alpha-9 and alpha-10 acetylcholine receptors at the same time, basically then started a decades-long collaboration between Paul and Belén Elgosian's lab in Argentina, really trying to understand how the mechanism at the efferent synapse involving this alpha-9 and alpha-10 receptor, these specialized acetylcholine receptors, operates. And I will leave all of that big story for next year. I just want to point out here's Paul, Eleonora Katz, Maru, and Belén Elgosian. It was kind of interesting, like we had like findings in 1 year, and in that same year, instead of in the lab kind of working this out, the methods were just handed over to some other group that then also further developed it. So this very open collaborative approach is just really amazing and now shows how highly productive it is. At this point, these two groups were at a point where they are were working on gene therapy approaches with a modified alpha-9 receptor to think about methods to prevent cochlear noise damage. And here I want to shortly point out every PI has a project which for a very long time just simply doesn't work, and the more experiments you do, the more deeper you dig your hole, and it gets very complicated and you simply can't interpret it. And I have watched Paul for many years working on what's called, has this beautiful name, the subsynaptic cistern, in that fashion, but just simply not being able to stop, right? Let me tell you what that is. At the efferent synapse, here this is an EM, you see the vesicles that have the acetylcholine. They will be released into the synaptic cleft. And then on the left side here is the hair cell. So this is the hair cell membrane. But then you see here another membrane and this white space. That is basically what's called the subsynaptic cistern, which is just sitting basically postsynaptically to the efferent fiber in the hair cell. adjacent to the at the synapse, and it's highly likely a calcium store. And Paul has spent many years with a number of publications, and there are a lot of unpublished data, where he tried to figure out how this subsynaptic cistern contributes to the calcium dynamic at the bottom of the hair cell, because it is very important what the calcium concentration is here, because the calcium activates these calcium-dependent potassium channels that hyperpolarize the hair cell and really change its properties. And the influx and efflux from the store is very important. And then secondly, they have also really studied how influx of calcium at the afferent synapse may affect the efferent function. I leave it with that. As I said, this is a very complicated story, but Paul never gave up on it and just didn't publish until he had the feeling he really understood what he was doing, and I really admire that. Finally, a topic in Paul's lab have been the outer hair cell synapses with type 2 auditory nerve fibers. We all know that 95% of afferents contact the inner hair cells, but 5% of afferent fibers contact the outer hair cells, and we really still don't know what they do. And the Fuchs lab, together with the graduate student Kat Weiss, now at the NIH, has provided the very first description of any activity in type 2 fibers, which was also published in Nature. And over the years, the laboratory has systematically worked on adding to our knowledge how these type 2 fibers operate, that basically they respond to damage through a purinergic mechanism. The lab has identified many markers that allow us now to manipulate these fibers in the future. And hypotheses have been developed, still to be proven, that these fibers may resemble pain fibers. Finally, Megan Bears-Wood and Nate Novak, which I know are in the room, have developed what they call a half-shell preparation, where with 2-photon imaging, they are able to now, with calcium imaging, look at type 2 fiber activity while they damage the outer hair cell area. And I think there is still a lot to be learned here. So that's my very quick run through research of someone who has, like, for 40 years, really moved things along. So now on a personal note. So here you see Paul and myself in our best outfits at the graduation, where we do at Hopkins black tie event. Well, and so I just, what have I really best learned from Paul that's really valuable, besides talking about research and, designing projects? I think it's really his mentoring and leadership style. So he is really someone who inspires students and teaches important principles. He creates a very supportive, positive environment, encourages collaboration and sharing, and really lets others follow their own vision, which is important. He plays the ukulele. I needed a short sentence there in the middle. So he is a very low-key, active listener. So you can come to his office and go on about stuff. He will not immediately say, you should do this. He will listen and then extract from what your plans are, what might be the right thing to advise. If you get into a fight with him, which I have, he reflects and compromises. So, he goes home 2 days, comes back, and comes up with a real compromise, which is very impressive. It's a very high level of integrity and civility, and always puts the greater good first. So here's my thing. I think he learned this from the hair cell, because the efferent synapse during development helps the afferent one to set up, and the afferent synapse provides calcium for the efferent to function. And I have coined a new term that's called synaptic transfusion. But wait, there's one last thing besides the science, one very long-lasting effect on the scientific community. Just it needs to be mentioned here, a huge accomplishment. While Paul was the president of ARO, he invented the hairball. Where's the music? There's supposed to be disco music. It obviously didn't work, but you can hear it. Anyways, thank you, Paul.
Wow, that was great. And there will be once he's able to speak, and there'll be another, next year we'll figure something out. Well, to be determined. While Rona comes up here for me to pass the gavel, as president, I'm going to pass the gavel to our incoming ARO president. Thank you, everyone. Congratulations again to all the awardees, recipients of the awards, and all the organization that went behind that. I welcome you all to a reception. I think it's in Crystal Ballroom A, B. If you want to talk to all the awardees and have a little wine and whatever they have going there, please come in. So with that, I would like to pass the gavel to Rona, our future president. Would you like to say
Thank you, Sunil. And just before we finish, maybe an opportunity to thank Sunil for all of your work this year and for setting up the ARO meeting. So let's give Sunil a round of applause.